were going to have Marby. Gordon Marby was going to be here in Buenos Aires. He was going to come to Argentina and also to other countries in the region. But unfortunately, he had some health problems. He is not going to be here with us today. It's not a serious problem, but he wasn't able to travel. So we have Rodrigo de la Parra, who is the Latin American and the Caribbean Vice President of ICANN. He's going to tell us a little bit about it, and we're also going to have Nicolas Antonello, who was a student at the school in Bogota. I remember we celebrated his birthday at the time. It was in April, and yeah, we had a couple of celebrations at school and then at night at dinner. And he's going to tell us some technical issues about the domain name system and the different activities of ICANN as regards that issue. I can't see anything here because of the lights, but I don't know if you already have your microphones on. Welcome, Rodrigo. Thank you for being here. First of all, he's a friend of us. He's from Mexico, a country we love. We want to go there in March, as always. Come here. So the floor is all yours. Thank you. Hello. It's a pleasure to be here in Buenos Aires. I love coming to Buenos Aires, and after not having the face-to-face meetings for a while, it's been kind of difficult, but I'm happy to be here now. And what we need to do is to be grateful that at least we could have online meetings during the pandemic. And of course, this has to do with the platforms such as Zoom or Google Meet or the other platforms. But there is something behind that is called internet. And thanks to internet, we were able to be communicated. And it was like a lifesaver, not only from the economic point of view, but also the social one and cultural one. It was really important to be able to have internet and to communicate. And that gives us the idea that this great technology that allowed us as a planet to be communicated even under such difficult circumstances. One of the most important messages is that we should not take it for granted. Many of us enjoy internet. We always have a connectivity, and when we don't, because of different reasons, is when we realized the importance of it. That's why to study and to analyze internet governance and their regulations is specifically important for us. And that's why in different fields we need to receive training about it, not only to learn, but also because the internet governance means doing things. It's not only, or as we have seen in the previous presentation, we have an invitation to be involved, to be engaged in internet governance. It doesn't matter if you work in the public or private sector, if you're a member of a civil organization, the academia. It's important to be part and to be involved in these decisions that are changing internet day by day. As Olga was saying, I work for ICANN, which is the organization that you have heard in the previous presentation as well. Have you learned all the acronyms already? We're going to give you a test on acronyms. In order to have lunch, you have to answer 10 acronyms that we have seen in Spanish and English, so that you learn to speak ICANNese, which is the language of acronyms. I'm going to try not to use so many acronyms. Acronyms are not very friendly, but I wanted to give you the presentation with Nico About ICANN in the Internet governance context. Why ICANN is an important organization as regards Internet governance. That is the first message. And then I also want to emphasize the technical role of Internet that is vital for the functioning of Internet, and that many governments, when they try to correct some Internet governance problems, may affect the technical functioning of the network. So we need to try to avoid that. Without getting into the specifics of the domain name functioning, we need to see that in ICANN we have two ends. One has to do with names and the other one with numbers in Internet. Nicolas is going to explain in detail the interaction between names and numbers in Internet and how does it help in general. And within that interaction, the important thing that we need to understand is that every time you want to send an email or to access a web page, or when you are using an app in your cell phones, what you are doing is using this domain name system. DNS are vital for Internet to work. Take that into account. And it is also vital to know that although ICANN has a vital role in the coordination of names and numbers on Internet, is not the only organization doing this. As regards the DNS, it is a global organization, a non-for-profit one, that globally coordinates many other organizations that make this possible. There are several coordination things that are involved here, and I'm sure that you have heard the name of the ecosystem. Thank you for turning on the lights. I can see the people now, the audience. There's an ecosystem with many organizations in Latin America and the Caribbean. There is one that is called LACNIC, which is the registry for IP addresses in Latin America and the Caribbean. Nico is going to talk about why these IP addresses are so important, and each device that is connected to the Internet, the computers, the cell phones, even a fridge nowadays, needs a number. It's like your cell phone number. In Internet, those are called IP addresses, and this is so that the machines can get to find each other on the Internet. That's why we have an important technical need to keep it stable. If this fails, nobody could meet on the Internet. And there's also a need to keep it homogeneous, so that it is the same for a user in Argentina, or maybe a government in Germany, or a business in Turkey, so that everybody uses these same numbers to be identified on the Internet. So from the technical point of view, I think that is clear why that is important. ICANN is important within the Internet governance context. But there are also two other factors that make it relevant. Back in 2003, 2005, within the context of a summit of the UN, which was the Information Society World Summit, when for the first time governments all over the world were asking themselves who was going to manage Internet. Take into account that we are talking 20 years back into the past. Internet was not the same, but it was showing kind of a potential of what was going to be like it is today. So governments were a little bit concerned about it, and actually there are millions of people that are behind this, using their computers, developing new things. For example, search engines. You have heard great stories about how Google or Twitter were developed, these great unicorns, even some Latin American unicorns. And the network is distributed everywhere. So it's not that there's a single person behind it. There are some organizations that operate this network and make it easy to have these business and social interactions. So when governments think about how they were going to control it and regulate it if it was everywhere, there were huge possibilities. And nowadays we are here after 14 years doing this Internet Governance School, trying to understand how we are going to tackle these challenges that we face, which evolve all the time. But in 2003, there was a group of organizations and a global organization that was called ICANN. And they said, well, they are the ones that are accountable for this. They are the ones who can switch internet on and off. It's not like that, but it was what was thought at the time. And behind ICANN, there was a contract with the US government, with the Department of Commerce. So for many other countries in the UN, the government of the US is not a very popular one. So they were saying, how come you have an exclusivity contract with ICANN, and ICANN is the one that manages IP addresses and domain names? It was not very clear. So they said, of course, we have to discuss internet governance and ICANN, and let's see how we can do it. So the fact that there was a contract with the US Chamber of Commerce, it was something that was because of the fact that first it was in the US where this was invented, and the DNS is a domain name system that Nico is going to explain in detail, make it that the regulation of internet was even thought about. So part of the discussion as regards internet governance at the time was focused on that. And the other thing, the other reason why ICANN is important for internet governance is that there is a model behind the ICANN that is a multi-stakeholder model. What it means is that all the stakeholders of the internet development should be invited to the discussion table. The private sector, civil sector, the academia, everybody should be part of this decision-making process. And ICANN already works like that. When it was created by the US government, they were saying, okay, maybe we shouldn't be managing the domain name system. We need to develop a global multi-stakeholder organization that could manage this. Thinking about what was going to be about internet in the future. That's why ICANN was created with these characteristics. Now Nico is going to explain how the DNS works. But I wanted to mention that ICANN at the time, it was about governance, but it paved the way for the internet governance guidelines to include this multi-stakeholder component that today still exists, because internet doesn't belong to a government or to a single person or a group of persons or to technicians operating it. Internet belongs to everybody, to the civil society, to users. You have heard the Lagralo colleagues, how they were part of the decisions. So think about it. Today, the internet governance agenda is comprehensive. Technical topics about internet are there, but are not the single topics that are discussed. In ICANN, we can talk about technical issues of domain and IP addresses, but there are other topics that maybe you are more familiar with, When we talk about internet governance, maybe we talk about privacy, human rights, free speech, economic issues, fraud, and many other topics. And in ICANN, we help learning about the technical functioning of internet and internet governance. Nico, why don't you come here so I can give you the floor? And let me tell you that when we try to find solutions to tackle some topics such as privacy, human rights, personal data, free speech, we need to consider that those solutions, when they are adopted, shouldn't damage the open architecture of internet. That is a message that I wanted to give you. Sometimes you need to think about maybe, I don't know, there's a privacy issue, so we should turn it off and that's it. No. We need to take into account that this is internet and it works. So thank you, Adriana and Olga, for the invitation. Also, Oscar. And I'm going to give the floor to Nico. Thank you. Nico, the floor is all yours to tell us a little bit about DNS. Can you hear me? Hello, my name is Nicolás Antoniello. I am the Technical Relations Regional Manager in ICANN. It is like the technical connection between ICANN and the different communities, considering all the stakeholders. As Nico was saying, it's not nice to have these lights in my face, but I think that you are there. I can't stay still, so I'm going to be moving all the time. I'm sorry. First of all, I want to give you a challenge. If you can, please shut down your computer and your phones. Many years ago, I went to a conference, and the speaker was a scientist leading the R&D group in IBM. It was based in Brazil. I don't know if they still have that. And he started his conference talking about sensor saturation,
which is signals sent to the brains from the five senses, and the brain becomes saturated as entertained with the signal of the five senses. The more I send, the more it becomes saturated. And at one point, I'm paying attention, but I'm not really paying attention. Not even what is in the cell phone or what I'm talking about. And if you can Twitter, you can Twitter later on. And if you have to work, okay, obviously, if it's urgent, there's no other way. Now, speaking of how the brain works, some years ago, when we started with the internet, or even before it was called or referred to as the internet, we're going to talk about the domain name system, but let me give you a brief breakdown, because the domain name system is even before, tracing back before the internet as such. And at one point, somebody realized that the human brain, for the majority, remembers sequence of words rather than sequence of numbers. In my case, this is true. I barely remember my cell phone and not everybody's cell phone. So I just look for the number, or I look for in my diary the last name, and I look for the phone number I just called. So basically, I speed dial that, and that is what I use in the telephony network for the telephone number to reconnect with another number. In the case of the internet, for devices to communicate with each other, to talk to each other, we use the equivalent of the same number, but to reroute IP addresses that are directly, or unique IP addresses that are redirecting devices like computers or whatever. So when I have to talk to a specific number, I don't know what I'm referring to. That's why we have that IP addresses or those protocols. And there's a protocol that is called EDICAS, that you assign the same address to one more device. Yes, that is existing, but it's an exception to a rule. We're not going to touch upon that topic, and that is specifically designed for a purpose that we are going to mention, or we are going to bring about in this talk. They have a unique address. What is a unique address? It's not called a telephone number, but it's called an IP address. And the directioning, or the IP address, currently and for more than 30 years, before the existence or the margins of the internet, you have IPv4 and IPv4 or IPv6. Okay, two different protocols. It's not the newer version. These are two different protocols because the basis of which for a protocol to have a new version is that the compatibility needs to go backwards. It cannot break or interrupt or discontinue the compatibility. Those protocols, they are not compatible with each other. You have a transition mechanism to interoperate between the protocols or to navigate an IPv6 or an IPv4 environment. Okay, but these are the two standards that are communicating with each other, or by these protocols, basically, they are able to interact. And somebody realized that it was easier to remember words rather than numbers, and that's why we have the emergence of the domain name system, or the DNS. The DNS is the version of the internet of the diaries. So the domain name system basically relies on a system that translates word sequences or domain names in our jargon that are sequence of words. Later we'll see how these are created, and the DNS translated that into an IPv4 or IPv6 addresses, and that's inversed lookups. I have the addresses and I want to know the domain name, the same as a phone book, like looking for a number and finding the last name, which is a little bit difficult in the telephony or the telephone book, but in the case of IP addresses, it's very easy. So here you have the emergence of the domain name system to translate DNS or domain names to characters. Laser, yes, works perfectly well. Very briefly, let's address some of the design or the architecture features for those people that standardized this DNS protocol. They thought that they were going to create a system such as this. So the DNS is like a large database, having special features that is distributed geographically. On the contrary to those databases reside on a single server in a single location or site, in the case of the DNS, the information lies in multiple servers, where every server has part of that information, and those servers are dispersed across the world. So this is a distributed database, and the other feature is the management of that database is distributed. So there's no single entity that manages and controls DNS, but the DNS is managed or administered by multiple entities. And there's a mechanism that there's an entity that manages part of the DNS can delegate to other entities the management of those of other parts of the DNS. So what is the architecture of DNS? Well, the composition is like this. This is called inverted tree. As you see, you have the roots, the branches, and the trunk. So it's inverted, okay? It's great that you have an LED, so if the laser doesn't work, I can point with my finger. So this is the root where the database starts. That's why it's called root. The root of the DNS is where you have the source of that, or the structure of that database that is branching out downwards. The rest of the structure, the DNS. So every single quadrant are called tiers. You have tier 0. That would be the root. It has no name. It has no name. There's no label. There's no way of defining the root. This is defined by a dot. And then we have a first tier, that is tier 1. Tier 1, or top level, that has every single node or every leaf in the tree that is labeled, okay? That label name is called domain name in theory. So what is a domain name? Domain name in the databases of DNS is the label assigned to a leaf in the tree. And you have different tiers. Top level, well, root is the root, node level, top level, second level, and third level. How many levels? Well, we can have 128 levels, which is useless because if I have a system to translate sequences of names of 2 IP addresses and I have 128 words long, it's impractical. Even in the standard establishes a limit, I could have a domain name that is totally qualified, and I could have a domain name at very low levels, like 100. It would be easy or easier to remember the IP address rather than the number, okay, or rather than the domain name. Excellent. Great. These domain names are super original. These are top level domain names. TLDL. So TLDs are top level domain names, and then second level, third level, and subsequently. So either we're going to highlight 2 or mention 2 of them. One is top level generic GLT, like .com, .org, .net, the generic ones, okay? And then we have the domain name or the top level domain names associated to country codes, like CC, TLDs, country code, TLD, top level domain names, okay? All of these rank in the top level of DNS. Then we have TLDs and GTLDs. And then we could have branching out as much as you can. The only condition is that every time I go down a level, every time I see or I go to the node, there's one connection. So if I stand on every single domain name, you have one parent, but you could have many branching out. I could have one parent and I could have innumerable branching out or branches, and I can designate whatever name I want. I cannot put two names or two same names. So you cannot have, if you have different children from different parents, you may have the same names. For example, here we have three with the same names. For example, they have the same label, www. And then you have the domain name that is totally qualified or fully qualified domain name. FQDN, I'm sure that you're aware of this, full qualified domain name. So that is merely the correct way of referring to a domain name. And that is not saying www. Why? Because the domain name that you said www, you say which one. So how are you going to refer to? Reading all the labels, scrolling down until the root separating every single label with a dot. And then you have everything that we know of, that is the totally qualified domain names or correctly qualified domain names. That is, if I would like to refer to this one in blue, the correct way would be www.example.com. That dot that is at the end is always there, even though it's usually suppressed. As it's always at the end, it's usually suppressed. We never mention the root, but from technically speaking, we have the root. So it's www.example.com, and we don't say final stop or final dot because there's always there. The same goes for mail. It would be mail.example.com, www.bar.com, etc. So we saw what a domain name is, and a domain name that is totally qualified. We have two definitions to go over. We've seen what a domain name is, and it's not the same thing. A domain is another thing. You have to read the label with the points. That is the main name. But what is a domain? Domain in the DNS is something different. It's any label that you may have and all the tree that is downwards. In this example, the domain.com, it would be the domain name com plus the whole tree that is downwards. Everything that is encompassed in the blue line. If I want to refer to the domain example, would be these three. These examples and downwards. In this case, you have this branching out. So domain name is a label and the whole tree downwards. And finally, I don't know if you remember that we said that the DNS is distributed geographically and the administration is in different locations. So the administration of these domain names is given to different organizations, and the administrative designation is called zone. So a zone is an administrative area. It's a set of domain names that are managed by the same entity. So that's a zone. Obviously, a certain entity could manage 1, 2, 3, 15 zones. However, this is a zone. This is just a division when it comes to management. In this example that we have to the right, covers a zone in the dotted line that is a root, where you have an entity, an organization responsible for managing the root, and that is responsible for the owner of the data in the root, and that organization is ICANN. ICANN is the organization that runs or manages, among other key roles, One of the key roles is to manage and control the routes of the DNS. And that's where we start with the tree of this database, and that's where you have the structure of the DNS. And the top level domain is delegated to the different domain names. There's one managing .com, .org, .net. It's not ICANN. The same is delegated to other organizations. Another organizations that may be private or public, depending on who has been delegated the management according to the country code in the different countries. In the case of NIC Argentina or NIC Argentina, manages .ar, and that it depends on the Foreign Office of Argentina. And in Uruguay, for example, this is managed by an agency of the University of the Republic of Uruguay. In some countries, this is managed by an academic organization. In others, managed by the state. Or by any organization. An ICANN, who's the parent of all the top-level domains, is the one that delegates in its children its management. And after the delegation of a top-level domain, the one that manages that top-level domain is the one that decides to whom and how the management is going to be done, everything that is subject to that domain. So if I delegate the management, that entity has the power later on to delegate the administration of their children. And this is what happens. So in this way, the management of the DNS is distributed. Do you have any questions so far? It's better if you interrupt me and not do it at the end. Please feel free to raise your hands, interrupt me. Let me take the questions, and then we continue. If not, it's going to be boring. Let's see how we resolve a domain name over the internet. In the browser, I type the URL. The domain name is part of the URL, and the browser should show the content of a website in the browser. Before we discuss this, we have two types of DNS servers. In the case of DNS servers, that is the equipment, the hardware, that provide this sort of service, you have two servers. One is that keeps the information or stores, that is for authoritarian servers. Those are the servers that store all this information or database that is distributed geographically. So all these servers that are distributed that store that information corresponding to every zone, this is called authoritative servers. They are the authority or the owners of the zone, and they decide the content and they delegate the management, etc. And then we have other type of servers that are called recursive servers or resolvers. Resolvers are servers responsible for seeking or looking for the information. Instead of the device looking for information or searching for the information, like the translation of an IP addresses, the resolvers are delegated with that information or with that power. So the resolvers need to know what IP address goes to the domain name. So it looks for the information in the authoritative servers, finds the information, and gives it to the handheld or to the device. So it's the one that stores. The resolver is the one that looks for. The authoritative is the one that saves the information in a server. Having said this, we have a resolution process. The resolver is the one that finds the information. And that has a special feature that is called cache memory. What is a cache memory in a resolver? It's always looking for this information for data and is retrieving that information to clients. And every time they find and retrieve that information, they save it in the memory. So if the same client asks for the same query, doesn't resolve it again. So they save that search. So that is part of the cache memory. It's not saved forever because the information changes. The server will never find out. So that information that is saved in the cache is for some time, and then it is erased. And if I perform the same query, the resolver finds the information again. But when you have that in cache memory, you accelerate the search process. That's why we have cache memory. Now, this picture comes from the site that is there in the link. So it's a screen capture of an example of the root servers and its distribution across the world. So that's a root, not the DNS branching out, just a root. So far, we had 1,557 root servers. That's just for the root zone. The 1,500 servers have exactly the same information, the same replication of information. So if a resolver performs a query, ask any of the 1,500 servers and it's the same answer. So what is the advantage of having a redundancy of the 1,500 copies? Well, it's more fault tolerant. If one copy fails, no problem. The resolver is going to find the query somewhere else. The 1,500 copies or servers will have to fail at the same time, and it never happened in the history of the internet. How do we update the root servers or the information saved in the 1,500 servers? How do we update these copies? Well, the DNS standard protocol foresees or provides a mechanism that is called XRT to transfer the zone in the servers. You can encrypt the information, it's safe information, so it's inbuilt the same protocol to synchronize and to make copies in between the servers. There's a fantasy of reality that Aboriginal peoples update more information than our information. This is the fantasy that we have over the internet across the world. No, it's not a fantasy, but it's not a reality 100% safe. It's not that if I turn on the knob or if I switch the lights, that the energy will arrive instantaneously. No, there's a light speed or the light speed, and then it hits the valve, and it's not instantaneously. With the DNS, it's exactly the same. The synchronization methodology is exactly the same. I mean, there's a sequence of data or updates, so it's not a centralized point in ICANN that immediately every server is updated at once, because some are farther than the rest. So where can I place this server, the primary server? And the redundant copies are secondary, and they are mirror effects of the primary ones. If I place a server in the United States, why? Because they are the ones that are the architects of the internet, and that's how they install it there. End of discussion, period. So the primary server is located there. If I have a single primary server, I have a problem. the rest of the copies are going to be outdated. That's why we don't have a single primary server. The information is copied from one location from the other, so there's a sequence of synchronization of data, and all the primary servers are synchronized first, and then it's distributed to the secondary servers, and then they're on, etc., etc., to cover the 1500 copies. It takes milliseconds to do that. So if I make adjustment, I make a query precisely in a millisecond, where there's an update in between the primary and the secondary server, I may receive a different answer of a non-existent domain name, but the browsers, they try again, and then they will see the answer. But it's not a zero chance that this will happen. It's not instantaneously either, but it's fast enough not to have that in practice of having something out of sync. We have geopolitical questions also. When we had 13 root servers, one in Japan and one in America, one somewhere else, that the servers, people believe that it has certain privileges over the rest, and that people would update those servers and not the rest. It's an old-fashioned kind of view, but there's always this question. Before I discuss further issues, let me take that question because it's a great question. Olga is right. It has a geopolitical meaning that becomes very relevant. When we invented DNS, we assigned 13 IP addresses for root servers. Originally, the standard of DNS provides 13 root servers and only 13 primary servers. And there were no secondary servers. Because we assigned 13 servers, we delegated the management of every single server to 12 organizations, because there's one that manages 2 servers, and that was the DNS. But internet was not called the internet at that time. So what happened later on? Well, we had the mechanisms to have replications or copies of the root servers. Each organization created or signed agreements with other additional organizations to host a server that would serve as a copy. So everything that is here, and I am sure that you see the distribution across the world, the 1500 are not copies of the same server. You have 1500 copies of the root servers, but some of them are the first of the 13 or the second of the 13 servers, etc., etc. And then people may argue geopolitically why we have 13 organizations that manage the root zone. It's not that we have 13. Here we're talking about the root zone. The rest is delegated to other entities. But yeah, this is the question, and there are 12 organizations that manage the root zone. Do they have control over the root zone? No, they don't. On the content they don't have control over it, because that is a responsibility of ICANN. So what ICANN does is ICANN supplies a copy of the root zone to every single organization, and the 12 organizations in turn submit the copy to the 1500 servers or copies that are distributed across the world. Who's responsible in ICANN to do this? There's an office in ICANN that is called IANA. IANA is responsible for producing or managing the information in the root zone. I am not going to explain how this works. It will take us a day to explain for the root zone, but there's a contract signed between an ICANN and a private organization that deals with the operation, the primary operation of the root zone that distributes to the rest of the 13 root servers, or the additional 12 servers, or 12 organizations that manage the root servers. One, or that organization is called VeriSign, who's the primary operator of the root zone. So VeriSign distributes that to the rest of the operators or carriers in secondary servers, and adding that accounts for 1,500 servers. And this is subject to any protocols, controls, surveillance, and any member of the community can have access to this information of public domain with all the checks and balances that are accessible for the global community of the internet to be connected or as safe as possible, that our queries are performed with transparency and with the necessary safety measures. And there's complexity embedded, obviously, and this works ever since the emergence of the internet. And there have been attacks and queries or hacking, but not a single time in the history of internet was the DNS discontinued. And this is a record for a system. There's no other system that hasn't had a total failure in more than 30 years. This is the only system that prevailed. It requires work from all of us, from the whole community. It's not just a technical aspect. It has a component, public policy, geopolitical components, and essentially a technical problem. Micrófono. Another question argued or posted by ICANN is, how can this system be vulnerable with quantum systems? I mean, there are no powerful systems that can make this vulnerable. And if there were, how would you protect geopolitically this system? The rest of the internet is going to hate you. I like addressing this, but this is going to take us up to dinner, not lunch. But let me mention this briefly. How do we relate computers with DNS? Or quantum computer with DNS? Let's see what a domain name is, domain name, and a zone, and how queries are performed in the database of DNS by resolvers finding the authoritative server's information until they find the answer. The only part that is missing in order to understand the DNS database is what type of information is saved and how. Is database having all the bells and whistles and the features, but we haven't seen the information in itself. The data that resides in the database is saved in registrations, or is a cell where I save the information, the data. So every zone that corresponds to domain names are going to have quadrants where I'm going to be, or slots where I'm going to save the information. What are the type of information that I can save? Primarily, there are two features: the IPv4 address associated to a domain name, and IPv4 or IPv6 associated to a domain name. These are the two types of registrations or types of information. These are the two information that can be saved in the DNS database. Why? Because we said that the DNS was a translation mechanism of names to IP addresses. But only IP addresses can be saved in the database. Also, an email, domain name, when you send, for example, an email, Mike says nicolas.antonielo@icon.com. There's nicolas.antonielo@ and the domain name or the domain where I have my emails. So my email is in the email server. So the email server corresponds to the domain that is icon.org. But the email server is not icon.org. Maybe it's email icon.org. So that is also saved in domain name server in a different system that is called MX. Then you have the IPv4, IPv6, everything that is associated to a domain name. MX saves the name of an email server. So it's a name associated to an email server. NS saves the authoritative DNS server so the resolver can find that and can perform the queries because it's the one that is saving the information that I'm looking for. PTR is inverted search. That's why I do inverse mapping. We're not going to explain how it works because it will take too much time. And the CNAME is to create alias. I could have a domain name, for example. If I were nicolasantonino.org, so I can create an alias that could be nicolas.org, and nicolas.org is an alias of nicolasantonino.org. So I could have the creation of alias as many as I want of the same domain name. So that refers to another domain name, basically. And there are many registrations, 64 types of information, different information that can be saved in DNS, more than 64 registrations of DNS that are possible. And that's why we save information. What is the resolution process like? Brief example. Here we have a device or a phone number. It doesn't look like an iPhone. It looks kind of old. The GUI is different. Probably it's an iPhone 2, iPhone 3. We have a telephone or smartphone with Safari, and then you type a domain in the browser. So part of it is domain. So I type Netflix.com, for example, and I want to be taken to Netflix to watch a movie. So what does a smartphone require to connect to Netflix and to show the option of those movies? It needs the IP address because the name by itself does nothing. It's like the name in a phone book. You need a number. So all the activity starts with the DNS search. That's why the importance of the DNS, and that's why it refers to as one of the critical mission systems of the internet. Because if the DNS is not working, the internet is not going to be stopped. Now, if the DNS is not working, internet cannot be used by anybody. Technically, it's not discontinued because nobody knows the IP addresses. We all know the names. And when I type a domain name, to have access to a website, I need to perform a query to find an IP address. So the device is going to send to a resolver that is pre-configured the query. So tell me what the IP address of www.example.com. The resolver has nothing in the memory, performs a query in the inverted tree. Where do you start? The authoritative servers. Which one? They need to find example.com. So when they know where to start, the query starts in the root servers. So they asked one of the 1500 servers, root servers, and they said, I would like to know what's the IP address of example.com. The root is not authoritative of example.com, it's just the parent of the .com. So the answer is not what I'm looking for. It's not going to provide me with the IP address. The authoritative server, when it doesn't know the answer, is going to approach as close as possible to that response. So the root knows who's managing the .com. So the root is going to reply to the resolver, look, I don't know what you're looking for. However, I can tell you who to ask. So the resolver finds the information and does the same or makes the same question to the GTLD. So the authoritative server doesn't know what the answer is, but is the parent of example.com. So I have .com, so this is the parent of example.com. So what is going to answer through the resolver? I can tell you who's the authoritative server of .com. So it asked the authoritative of example.com, and now that server has the information for www.example.com because one is the parent of the other. It's like a tongue twister, but probably you can study that at home, you can do your homework, and it's so boring that you're going to fall asleep. So the authoritative server of example.com bears that information and answers with the IP address associated with example.com. The resolver saves that into the memory, sends the information to the browser, and the browser has the IP address, goes to the website, downloads the website, end of search of DNS. And then we have the view of the website. Then you have any kind, the same goes for any activity. First, it starts with the query of the DNS, and there you see the critical application of the DNS or the domain name system. Let me briefly address this. I'm going to give you some of the headlines. The protocol is this one. The original protocol did not consider many things like privacy, security, etc., that they were very important and increasingly more important because the internet worked with the goodwill of users or with the community. Just a few organizations and connected servers or what we call the internet. We have hundreds of millions right now with different ends, purposes that we have the good guys and the evil or the bad guys. But this works the opposite. Hackers are one step forward and we are staying behind, so we try to catch up. We have breach problems. So to the protocol, we added other protocols that became standardized that add functionalities or features to the DNS. Let me mention very briefly what these are, and let me review and go over them. See, this that is here is a scheme of the whole DNS ecosystem, is what Rodrigo said, the clients, the recursive servers, the authoritative servers, the registrations, the registrants, etc., the clients.
We use this so that you can see each protocol. And these protocols don't compete between each other. These are complementary. So the idea would be to implement the most we can to add privacy resilience to the domain name system. There is a protocol that is called DNSSEC that acts between authoritative and recursive servers. What does this protocol do? Basically, remember the answer of the authoritative to the recursive. Well, that answer, when I have DNSSEC enabled, sends an electronic signature of the answer. And the recursive, which receives the information, can check the signature and to know if the answer is a real one or if it is a fake. Here we have quantic computing. DNSSEC is based on encryption algorithms, public and private key, for the computing capacity of a supercomputer that works in the same way that in computers today, which is not quantic computing. The difference between quantum and current computing is that What quantum computer is offering is that the speed for certain mathematical operations that a processor in the computer does is going to be several million times higher. So maybe an operation that takes 100 years for a computer those operations are the ones that would be necessary to break an encryption system like this that DNS is using. And a quantum computer can solve it in a few seconds. So that is going to be a problem. If I can break an encryption code in a few seconds, it's a problem. So what we are working on, and there are some proposals, is encryption systems using algorithms that won't be broken by quantum computers. This is being developed. Anyway, quantum computing that would be accessible and effective is going to take a few more years, probably more than 5 to 10 years. But nevertheless, these algorithms are being developed so as to be ready when it's necessary. So imagine this at the global level. Basically, electronic safety, security is going to change. Goodbye credit cards, encryption, VPNs, DNS-sec. After quantum computers start being sold, these algorithms are being developed and probably are going to be produced at all levels before that technology is available. So don't worry. We know what we have to do. So the best algorithms needs to be defined, tested, and implemented. Security algorithms change all the time. The first ones are already obsolete, so this is an evolving thing, so it's not news, it's not something that was not done, even if it sounds like the far future, it's something that is simple. That is DNS-sec. Privacy. There are two protocols, DO8 and DOT, on HTTPS and TLS. These are protocols that contribute to the DNS. DO8 offers privacy between the customer's device, and the recursive server. That first thing that the client sends to the recursive goes through a clear text. If that is captured by somebody, they could know where I want to go. So what DO8 or DOT does is to encrypt the communication between the customer and the recursive server. So it offers privacy. Nobody can know the DNS that I'm asking for. And this will give privacy. There are other protocols that are between the authoritative and the recursive that offer privacy between the recursive and the authoritative server, and that is called minimization or QNAME minimization. Remember that the recursive server is always asking all the name. So if I activate this protocol, the recursive is going to ask the authoritative what it needs to answer. So it may ask only who is managing the .com. So the server won't know what I'm doing on the internet. In the example that I showed you, the root server won't know that I'm looking for the IP address of www.example.com because it will only send what it needs to be answered. That's why it's called queue name minimization. This is based on privacy by giving the less information necessary. It's a standardized protocol that can be enabled. We're not talking about hyperlocal, so I'm going to share the presentation so you can read it. A round of applause for Nico, please. Thank you so much, Nico. Incredible. If you want to ask questions during the lunch break, because we don't have much time and we are going to be starting the next panel half hour later. So we have to be quick with lunch. We need to start the next panel at 1 o'clock. So Karina, I have already told the rest of the panelists that we are a little bit behind. I hope that that's not a problem. And then in the afternoon, we are going to be able to keep up with the agenda. So let's get a picture of the icon, friends, and we already have the lunch break. So see you after lunch.